I declare quorum. I think we have enough to start. All right, so welcome everybody. This is Open Research Institute's Projects Meetup for April 7th, 2026. And what we do at this meeting is talk about what we have done, what we have planned to do, if we need any resources from ORI or anything we can help you get, and if there's any roadblocks, anything in your way. What we do is open source digital radio work, and we try to help people get the very most out of citizen science and amateur radio and digital radio. So what I'd like to share, what I have here on the screen right now, is some results. These are from Bochum. AMSAT DL has a large dish in Germany, and they use it for citizen science education and amateur radio. And Dwingalo has a large dish in the Netherlands, and they use it for the same reasons for amateur radio, amateur satellite, and for education and outreach citizen science. And the two dishes combined together, and what they did is in advance of the Artemis attempt, because both of them were very interested and were accepted into the sort of the Artemis observation program, they decided to kind of like work together and point at a quasar. And what they did is successfully got it worked out. And so this is the results of that target, and good stuff. All right, and then so there's been some published results for the Artemis mission from Bochum, and I'd like to show this because this is Artemis 2, and the predicted versus the measured for Doppler is pretty much identical. So you can see that their results coming in so far have been very, very good. These are initial results, and the mission is going to go on for another number of days. So it's about a little bit over halfway completed. Here's another image from Bochum. This is what the signal looks like from their dish. On the upper left, you can see what the dish actually looks like. It's large, and it's in a inflated radome. It's really pretty neat. And there's a museum inside the radome at the base of the dish. And here's one more image from Bochum, and that's what this looks like when you hear about Artemis in the news and the different stations that are reporting back. This is what's going on. Some OpenCPI updates from Aaron. You have the floor.
Thank you, Michelle. And it's been really exciting watching the Artemis 2. Been been closely monitoring that as well. As far as what I've been up to lately, I've been heavily working on Opulent Voice. Part of the Hyperia side of the satellite is to receive Opulent Voice data. And part of that is the channelizer. I have a set of slides here. So I've been working on a third implementation of the modem that's compatible with the other two. I call it Charlie, Alpha being the Pluto MSK, Bravo is the C++ implementation, and then Charlie is the one I'm currently working on. I've got it working end-to-end using interlocutor to generate data. And I got it working simulation-wise. Let me pull up my slides. Give me a second. And I've been integrating it with OpenCPI. Let's see. Can you guys see that?
Yeah, it's coming up right now.
Okay.
Yes.
So this is what the transmitter looked like. It's a little bit different. I'm not using the modulator. The existing one, so this is a new implementation. All the coding is done in software right now, and the MSK modulator. What I guess I'm introducing to the team today is half science, so doing some pulse shaping to the MSK. It's the way I've designing it is that it's still compatible. It's not a requirement, but it makes the receiver side a little bit easier when I get to that in a second. And it uses a single NCO versus using the three NCOs. And so essentially, let's see. Okay, so this is what the modulator looks like right now. Kind of the other design choices is that it kind of keeps with the back pressure and the sample rate, so it's not taken from the other NCOs like the other implementation. The receive chain, so this is taking into account the 64 polyphase channelizer. The idea is to get 10 megasamples per second, and I brought this up a couple of weeks ago. That we don't have a lot of samples to spare. It's about 2.88 samples per symbol in this configuration based on the symbol rate that we've chosen. I implement a burst detector for each of those channels so that we're not doing any of the demodulation or any of our timing is not corrupted by no signal at all. So after it detects a burst within the channel, the receive chain is gated that way, and then allows the rest of it to function. The next bit is a polyphase match filter. So this allows us to phase shift and correct the symbol, synchronize to the transmitted signal. And then the time and error detect is using a Gardner. And some of these pieces, like the NCO and the are the same modules that were created with ORI, the Matthews work. So some of that is being reused in this implementation. And then we do a decision, take the bits, and then a frame sync, and then we go through all the other framing stuff that already currently exists. So this is kind of like a zoomed in version and how they're connected. So the Pi controller is being reused. And so this works in simulation using GHDL and offsetting the timing a little bit to make sure that it converges correctly. So kind of the differences right now, the existing is the flat MSK or rectangular pulse. We choose two different frequencies. So this is half sine. Again, that's just to ease a little bit of the Gardner time and error detection that it's and the match filter here. We do, if we were to use this receiver against the rectangular one, it's still, well, I haven't tested yet, but one of my things is going to test it. We just take a 1 dB hit, whether it's shaped or not, or on the transmitted side. So this is what it looks like. The existing one, this is taken from the C++ modulation. And then this is the shaped one. But the reason I bring that up is because the spectral density, the whole point of shaping it is to make sure that the energy is in the channel of interest. So these orange grayed areas are the channel edges. So in the channelized portion, this would be essentially another channel. So we're trying to concentrate as much energy in the focused area there. So again, I guess bringing it up, I think we've talked about it, adding some shaping to it or not. But so this is another picture of it with the adjacent channels pictured here. On the left is the rectangular, and as you can see, it kind of goes into the adjacent channel. I guess we can pick not use adjacent channels, so we have more leeway, but when we get there, but this is kind of the idea of that I'm trying to utilize all available 64 channels. On the right is the half sine MSK. I think that's the last slide. But anyway, the idea is as I'm working through this through Charlie is to maintain compatibility with Alpha and Bravo and make it achievable, not achievable, because I guess we can still implement the Alpha one, but as a whole system, Alpha High Faria, trying to get it what it's going to look like. I don't know if anybody has any questions, but that's what I've been working on. So I guess I did have some roadblocks. So I was able to build the C++ implementation. I was able to get that working end to end using loopback. I did try to get the Pluto MSK, but I ran into some errors building the SD image. I know you guys were busy with BSides. So I guess make some reports on some of the roadblocks I hit on trying to build the Libra SDR SD card image that had that the HDL implementation, so that I can use as another receiver to test as I'm building this and putting this together.
Yes, yeah, please, if it's the easiest to file like an issue on the repository about a problem, then
Mhm.
please feel free to record it as an issue and just data dump like, here's all the error messages, here's the log, here's what I did. And that's very welcome and appreciated. And the image that you have on the screen right now is really telling. So this is a very interesting difference between the construction of the signal that we're using in the half sign MSK, which is also valid. There's a pretty good paper that walks through the 7 different ways you can do MSK. It's like enter the octagon sort of type of paper. And when I first read the paper, I was like, oh, it's just 7 different ways to do the exact same thing. It actually now is pretty clear that some of the choices for how to implement minimum shift keying fundamentally change the signal. Like I'm seeing differences in where the null to null is in the two implementations. And to me, that's very interesting and also has an immediate effect here. You can see how the interchannel relationships change visually. You can clearly see it here on the screen. Um, so this is well worth digging into and finding like, do we need to revise our channel map? Do we need to figure out how to define it? Do we need to tighten up the definition of what MSK means? And all of this stuff is things that you've raised with Charlie. So these is extremely valuable work and a really beautiful image that tells us a lot.
So more to come. I guess what I'll be working on this coming week is taking the simulate what I have in working in simulation and getting it to work on hardware and see how far I can take it within
Right.
this next coming week.
Yes. It's always a great adventure.
Yeah.
We're
I have
having
a,
a,
s-
oh, go ahead, Paul.
I have a small question about this picture that we're looking at. I, on both the flat MSK and the half sign MSK, on every main lobe, there's a little notch right in the center, and I've never seen that in the lab. Um, do you know what's going on with that?
I do not know. This is the flat MSK is just the output straight from the C++ implementation. And I'm just plotting it out. I did notice that as well. There's only 10,000 samples, I think, plotted here before it ran into the FFT. But I did notice that as well, and I do not know where that's coming from.
Interesting.
I think it's more prevalent here.
Yeah, I'll go look as well. I'll try to track it down. Yeah. Like to me, the immediate thing that pops out to me is the null to null, the difference in the null to null
So
frequency.
that there was a difference in the I and Q. I think it's swapped. I noticed that it was swapped in one places, and I think it's swapped here. So that might be a tribute to why the null to null is a little bit different.
Oh, okay. So I won't get too
Yeah,
worried until we nail it down. We will
yeah.
iron these things out. But for the most part, this is a huge help. Um, And yeah, the interoperability is where you learn the most. So when we hooked up the Pluto version or the C++ version to the VHDL, I think we've now found we've made 4 major improvements pretty much spread between them. So interoperability is where it's at. This is where the rubber meets the road and your specification actually is useful and can be duplicated and a multiple number of implementations actually happen. This is where you learn where you've fallen short in your description and where you need to specify things or bring out requirements. So this is extremely valuable work and very deeply appreciated. Cool. All right, so over the next week, it sounds like more. It tastes like more.
Mhm.
Awesome. Thank you so much. Is there anything that we can get for you or any resources that you might need or?
I think maybe if instead of me trying to build it from scratch for the Libra SDR, if I can get a known working SD card image, so that I can get that implementation running as another receiver for interoperability testing.
Okay. All right. I'm going to write that down and we will make that happen. I think that because our usual workflow is to go ahead and make the build.
Hmm. Oh yeah, I'll make those reports then on where
Yeah.
I'm stumbling
Yeah, please
on
do.
GitHub.
And yeah, and then we can add the because I do the make and then I go in and do make SDIMG in the make script and it just
Hmm.
makes the SD card image in the build directory. But I'm not sure that we are totally clear about that, and we could probably do a better job of just going ahead and publishing the SD card image with every revision of the Pluto MSK repository that like as a release. Maybe that would be maybe now is the right time to make that step.
Yeah, yeah, that might be helpful. But I know you'll probably report on that's the stuff I've been seeing on Slack on on that progress as well. So
Oh yeah. Yeah, there's plenty to talk about. Yeah, thank you so much, Aaron. This really helps because all of this is directly applicable to not just the terrestrial version and just getting Opulent Voice working, but the work that you're doing is critical to the satellite. So it's just super appreciated. Thank you so much.
welcome.
Let's see. So the next thing I have on the update is Opulent Voice demonstrations, but I see that Thomas Telkamp is here. So I'd like to go ahead and jump forward to the Earth, Venus, Earth link analysis. I'm pretty sure Thomas probably has some news, and because we showed a little bit about the AMSAT DL and Dwingalo collaboration on the astronomy targets and also the work on Artemis. So I'd like to go ahead and turn the floor over to Thomas if he has any things to report or any particular questions, anything that you'd like to know about. We do have a lot to report on Eve and a link analysis, but you have the floor first.
Yeah, well, I actually came to hear your story about the update on the Eve. So I really have not spent any time on that yet because we're so busy with Artemis, which is a few more days, and then we can move to the next target. But indeed, as part of this, we're doing some things together with the 20-meter dish in Bochum on S-band. And we have done some VLBI on quasars, but also on Artemis. That was the whole purpose. And last night we combined them, so we observed a few strong quasars just before Artemis was above the horizon, and then with continuous phase moved to Artemis, such that we had a phase calibration for the Artemis measurements. But there's still some things to work out there. But it was a nice opportunity to just try this and see how far we could get. But it did work quite well. But I have not prepared anything else.
Oh, okay. No, that's plenty. We're really enjoying the all the results that we're seeing. We really appreciate the reports, and I'm looking forward to hearing like the full story after everything is over. I know that it's very busy and not a whole lot of time for writing at length, but we're really looking forward to hearing about all of the success and what it took and the lessons learned, what we can use moving forward. So thank you so much, Thomas.
Okay, I'll do. Yep.
Okay, so yeah, we can talk about the Eve link analysis. So some good news. We're increasingly confident that the improved carrier to noise ratios that we're getting from the Eve link analysis are real because they match up with other work that we're digging through the literature to find and just matching up with the radar equation in general. So what we're looking at is for a dish such as Bochum, such as Dwingalo, around about 0 dB for the carrier to noise ratio in 1 hertz. This is a big improvement from which we were talking like -8 down to -10 before. And the reason for this discrepancy was a sign error in the link analysis. And so you just have to keep working your budget and keep working your code and keep at it. And we did eventually find why it was so pessimistic. Now, it's still very challenging, getting this
Can I ask,
additional. Oh, go ahead.
apologies, I've browsed through your notebook, but I've not read it in detail. But where does the difference come from? Because these are not the numbers we have measured, right? This is.
Yeah, now the numbers match the CAMRAS data. So we were wondering why the data from March 2025 looked so good and our budget was so pessimistic. And now it matches exactly the results that you got at Dwingalo.
But we didn't see a 0 dB carrier to noise ratio in 1 hertz.
No, when you normalize it out though, it does equal. So it's now the same as what you saw.
Okay, I'll have a look at it. That's better. Yeah.
Yeah, and I'll write out something a little more lengthy and point to it. So it was a big relief because our numbers were very pessimistic. But now they line up with Dr. Estefe's results and the data that's published from CAMRAS. So we're increasingly confident, but there could still be some bugs in there. So we're trying very hard to make sure that it's accurate. Because what we're doing is we're reaching out and asking for time on some of the scientific instruments that are available to institutions. So we've applied for time at Green Bank Observatory for the inferior conjunction, so that Green Bank Observatory, which is receive only, but it's a 100-meter dish, will be available for a series of windows, starting before the conjunction and then continuing slightly after. So this will be like 3 weekends worth, 4 sessions spread out over 3 weeks to kind of catch before and after. And we're also in the process of applying for time at Effelsburg, which is another steerable 100-meter dish with very similar abilities. And so what this gives you when you go from about 20 meters to about 100 meters is another, I think, 12 dB. So if we in other words, we're going to try everything. We're going to continue to refine our link analysis. We're working very hard on the Zadov-Chu. Pete Wyckoff is the one that has done the most work on the Zadov-Chu, and we are doing some work with this channel, which, as you all know, is constrained by the coherence time because of the Doppler spread. Most of information theory work has to do with capacity equations, or you've heard of the Shannon limit, and this assumes an infinite coherence time. You don't ever have to worry about this stuff when you come up with your DVB-S2 curves. So if you've done DVB-S2 work or any sort of digital signals work, you know that the Shannon limit is the limit. Okay, so what happens when you have finite coherence time? What happens when you have a coherence time that's actually pretty close to your symbol length? And guess what? We have that here. We have a coherence time that is real, a real threat to us. It actually does limit it. Well, there isn't really a nice, easy set of equations for that, but we're going to come up with them. So what Pete has done is done a lot of simulation work where you have, Doppler spread, you have a limit on your coherence time. And guess what? It actually does behave in a predictable way. So we're going to write this all up and put it down into a set of curves. And we're pretty confident that we can come up with a Zadov-Chu communication scheme that will dig out of the noise and will provide a way to communicate through the Earth-Venus-Earth channel. Whether it is -10 or 0 or +10 dB, I think that we can pick the chip rate, and that will give us essentially a throughput. So it's very similar to sort of traditional communications, digital communications, but it's designed for a channel that has a significant Doppler spread. The results at 1299.5 megahertz were plus or minus 0.75 hertz Doppler spread. And this scales linearly. So when you go up to 2304 megahertz, you're going to get, more. And we're going to design for that as well as the 1299. And also for lower frequencies as well, just as kind of a test. And so all of this will be in an article or in a paper. And all of this is open source, so if there's a mistake in there, then we would really like for people to find it. The root cause of our previous, kind of conservative numbers for the carrier to noise ratio related to how we handled albedo and reflectivity. And we were taking away, essentially, minusing a negative. And, it was already negative, and when you do that, and it came at a critical point in the notebook. So that's exactly where it was. We found another sort of lesser problem that did not go into our favor. It was related to another part of the notebook. And this is just, you need to have multiple people, independent people reviewing your work and finding these sorts of things. So that's kind of the big major updates. What we'd really like to do, and what I've proposed back to Pete, is if you have a Zadov-Chu in sort of style, construction of communications, can we do a channel sounding first, like you do in other schemes? For OFDM, for example, you're constantly doing a channel sounding and you're constantly equalizing your multi-carrier OFDM signal. Can we go ahead and transmit something loud and then get back? Here's how the channel is right now, and then adjust the Zadov-Chu communications to that particular dish, that particular attempt, that particular 4-minute transmission. Because I'm assuming that most people want to transmit 4 minutes and then wait 4 minutes for their full echo to give you the most amount of time to do first your coherent and then your non-coherent integration. If you can tune it for that day, for that particular albedo, for that particular moment, then, that particular altitude, that particular distance to Venus, then I think you'll have the very best chance of getting through some number of bits. What we're looking at is between 0.1 and 1 bit per second. So these are very low bit rates, but they're real bit rates. We can actually get through communications, and it's a reasonable coherence time or integration time, a reasonable integration time, so not 13 hours, but less than that. So that's where we're at today. And we're trying to work very, very hard on this as early as possible to give the best possible chance to everybody that wants to do communications attempt through EVE. Adding dishes like Green Bank Observatory, if they agree to the proposal. This is we're asking through the director's discretionary time program. And Effelsburg, we're just applying, and Effelsburg is very open to anyone applying for reasonable use of their dish. 100-meter dish gives us the best possible, sort of listening partner. So even if you can't hear your own, or someone else can't hear your signal, if it was almost good enough, marginal, if we blew the link budget, if things were just bad that day, then with a 100-meter dish and a recording during these 3 or 4, sessions, then we have another way to catch all of the signals and say, here's all of the attempts, look at these. And then we would be able to do that. We're going to have to pick $12.99 versus $23.04. And what I've come up with so far is to alternate over the weekends. Another thing we found out from really digging in with the link analysis is that the best day is actually the 25th. That's technically not the inferior conjunction, but because the albedo is getting better and better, because we did the dynamic albedo, we added that to the link analysis. We take the reflectivity map of Venus, we plot the actual point that's facing Earth. We integrate all of the pixels on the dish. We do like the center part, the suborbital part facing you matters the most, and it kind of like goes out almost at a Gaussian curve. So we do all that for you in the link analysis. We show you what the albedo really is. You don't have to use a static number because albedo is increasing throughout the inferior conjunction, and a little bit after. The October 25th actually is the best day, and October 22nd, 23rd. So we pick both of those, the whole window, and split up the frequencies alternating back and forth. So if you have 12 1299, you get 2 out of the 4 chances. If you have 2304, 2 out of the 4 chances. Okay, so that's what we're trying to coordinate and trying to provide to give a really good receiver. Maybe if we're really lucky, both of these big dishes will agree to the proposal for citizen science work and provide recordings back to us so that we can then immediately post them. Like, here you go. If your signal is in here, go ahead and see if you can get it. And we'll, of course, do that work ourselves, but we're going to share all of this work immediately with everybody. All right, questions? I know it's a lot. Questions or comments about any of that?
No, very interesting work. So looking forward to the details. So you mentioned a bit rate of 1 bit per second and going down a bit. Is that assuming the 100-meter dish?
No, that was just assuming that we would get somewhere near -1 dB. You know, that's assuming like -1 dB in 1 hertz CNR. And that means a lot of things. And actually, the CNR doesn't matter for a lot, but if you can get close to that or around to that, 1,000 hertz chip rate is where you're at. You want to bracket you have 2 brackets. You have these physical limits above and below this communications attempt with ZOF2. And so we're just going to hit them right in the middle of the road. And yeah, and it depends really on the Doppler spread. So that's what's really kind of limiting your throughput is the Doppler spread and how you construct the signal to deal with it. And it's either, at the very best case, if there was half a hertz Doppler spread, you could get about a bit per second. But I told Pete that's too optimistic. That's not that we're going to get at 1299. We're probably going to see the same Doppler spread, 0.7 plus or minus 0.75 or 1.5 hertz. And at 2304, it's going to be 2.66 hertz for Doppler spread. And so when you do that, when you go up in frequency, this Doppler spread also goes up, and that does impact the throughput. So that's what we're seeing today. Still not bad. Better than 1 bit per hour.
It sounds very high to me compared to what we have seen when we tried this. I mean, we took 5 minutes to sometimes see a carrier.
Mm-hmm. Well, for the CAMRAS data, for the 4 minutes, the carrier actually comes up pretty, you start to see it fairly quickly. So the rate of acquisition is not bad in the CAMRAS data.
No, okay. One bit per second is still a lot.
1 bit per second sounds really low, and it's actually too high for, that's peak picking, half a hertz Doppler spread. That was, he was like, oh, sure, half hertz. Okay, that's too optimistic, Pete. So, I gave him the actual observed results from Dr. Estepa's analysis of the CAMRAS data. And then if you're going to go to 2304, well, it's going to scale up, and that actually starts to impact your, so all else being equal, what we really are going to have to do is design, here's the correct ZOF2 for 1299. Here's the correct ZOF2 for 2304. I think that's what we're going to have to do. That it can't be the same for both, because you have things that are shifting. And what really matters for this channel is the Doppler spread. That really, really limits you. It's not like a normal terrestrial channel. And it's difficult to get your mind around it, coming from a background where you have unlimited coherence time. That's not a factor in dealing with Shannon, but it is here. And
it's really unfortunate that our ZOF2 failed. Actually, the transmitter failed exactly when we started to transmit the ZOF2s. Otherwise, we would have had at least some data points now. And I wish I had changed the order. At least we would have had 1 data point, but it's too late now.
I think that your order was right. I think that you should start with the most sure bet. I don't think it was wrong. Maybe alternating back and forth would have been okay, but I think that your order was right and your instincts were right, and you got excellent, amazing results. And we all try to be perfect, but it's so you're being a little too hard on yourself. I think that was the right order. That was the good thing to pick. And what we can do right now with the results that we have is to try some EME, turn the power down and try to duplicate it. We won't have the limits of the Doppler spread, but we will be able to kind of prove out the rest of it.
Yeah.
So that would be the next thing to do as soon as Pete's ready. We're going to double check. And I take your kind of caution about, oh, wow, now sounds a little too optimistic. Your caution's well taken. So I think we'll just keep reviewing this to make sure that we've got it right. It does jive up with some of the Russian results. It jives with with the radar equation in general, but still, we trust your instincts and your advice. All right. Any other questions about Eve or any comments or?
I had Michelle, this is Adrian.
Hey,
I just
Adrian.
have this kind of a really crazy idea, okay? It just popped in my head. You're talking about the Doppler problem. And if you're doing moon bounce to try to simulate something akin to what you'll be seeing during Eve, okay, this is really crazy, unworkable. If you had enough of a sharp enough antenna beam, if you tried to project to the limb of the moon so that you get the maximum libration sort of
Oh,
rotation of the moon
yeah.
to sort of simulate a larger Doppler echo from the moon, would that be even workable? Sorry.
No, it might be. Usually the beam width is the problem
Yeah,
because if you're just illuminating the entire disk, then it doesn't matter where you're pointing really. But
right.
your instincts are good. We're trying to set up the same sort of physical situation that we would to get some practice, some real practice with real antennas. Because going back to Artemis, just trying to track the Doppler of over a 10-day mission. Like Loretta is one of the stations for Artemis and has had a series of RF failures. So all sorts of interesting things happen when you're actually trying to point things at, point actual radios at things. And we really, really do need to practice. And EME is an obvious candidate for testing out this stuff, turn the power down, make the link look similar. The thing that you're missing is the Doppler spread, but Moon has libration, which for those that don't know, the Moon actually does wobble around a little bit. But for the challenge there would be trying to duplicate the beam width or trying to get it to focus on the point that's librating to you. So good idea. I'm not sure we can set up an actual physical thing that would do it. But yeah, your point's well taken, and that's the thing that we have to kind of worry about the most. Well, along with all the other stuff like the daunting path loss and and the fact that you have to construct a real honest to goodness transmitter amplifier, anything in the 1,000+ watt at microwave is not easy. As we've seen, this has been one of the trickier parts where transmitters have caused a lot of trouble. We've moved the Eve link budget or link analysis document to its own repository, so it's easier to find. It's at Open Research Institute's GitHub it's capital EVE. So it's its own repository with an additional, and also the addition of the dynamic albedo calculator was really cool. Thank you very much to John. He's not here today, but he was the one that suggested this, figured out how to do it. It's all open databases from NASA. The Horizon database is one that we used. We used a published NASA reflectivity map. And what we do is, to given a date and given the reflectivity map of Venus, there's only a few chunks missing, so the survey did fail in a few places. You can see where they ran out of oomph. But what we do is we take that reflectivity map, we figure out what longitude, what's your suborbital point based on your radio location in the link budget. Oh my, I don't know. Okay, so there's some sort of fireworks behind me. I don't know how that happened, but anyway, so what we do is, so we have this reflectivity map, we know the date, we can get the longitude, we know your location on the Earth, we match everything up, we integrate all the pixels, and we use a model that actually jives with albedo return from other missions, because the points that are facing you directly are the ones that matter the most. The ones out on the limb matter less and less and less for reflectivity. What we have found is that the albedo, the static albedo number that we were just using for the entire planet is too high for the dates that we're talking about. And we lose a little bit over a dB. So we have that loss tracked and shown to you in the link analysis. It is trending upward towards and through the inferior conjunction. That's the good news. So we now know what the actual, to the best of our knowledge, the actual albedo for that particular day. So dynamic albedo mapping is something that's now in the link analysis, and this helps. So it makes about a dB difference. And the maps are really cool looking. We've learned all sorts of stuff. There's some very bright parts of Venus when it comes to albedo at around 2 gig, because that's where the maps were taken. And there's a part of Venus that if we were looking right at it, the albedo would go up to nearly 0.5. Right now, we're dealing from about 11% up to 13, 15%. But, upwards to 40%, it would be a huge deal if we could do it. Unfortunately, that really bright spot is up in a northern latitude. It's way high up. We'd never really see it from any place on Earth, but there it is. There is, however, one that's almost at the equator, and it does roll by every now and then, and it's really kind of close to us. So it's almost making it towards us for October. So the open question that we haven't answered yet is to ratchet ahead to the next one, 18 months from October, and see what the albedo looks like there. So that's a new thing that's in the link analysis, is the dynamic albedo mapping function.
So I have one question about it, and again, apologies, I've not read the details, so maybe this is obvious, but these bright spots, they have been seen by radar when they are somewhere on the side. So you basically see the side of the mountain, and then you see that showing up as a bright spot on the radar. But if it's at your sub-Venus point, or how do you call that, then you're looking at these mountains from the top. So you're looking at a different angle than where they have been measured. So is the albedo the same then?
Yeah. So the survey is straight on. So the survey is giving you the actual value as if you were looking at it.
So they have already made that calculation to the...
Yes, for almost all of Venus. Now, again, the survey is incomplete. You can see in the maps when they're in the link budget when you run it. So the map, when you see the map, you can see that there's some dark stripes where they weren't quite able to get all of Venus. But when they mapped the reflectivity, these surveys were done not from an angle, but these are the true, this is the reflectivity at, how would you say, when it's looking right at it. So as accurate as possible.
Okay.
Yeah, so we don't have to guess. It wasn't just a snapshot and then some of it's at an angle, because yes, you're correct. That would be way off. So these are actual reflectivity surveys done with a particular mission. Yeah, the citations are in there, and you can go look at the website and you can type in the date and get numbers yourself. You download the maps and there's a fairly, I would say, to me, it was a complicated API, and most of the work for getting this to work was figuring out that east and west, or east and west, and getting the coordinate system to kind of like cooperate. So the coordinate system from, hey, what side of Venus is facing me versus, hey, where is that on the map? That took some doing. So again, it's all in there in the link analysis, and I think it matches up when you go manually check and get a result. So it seems to be accurate now. For a while, I had east and west completely reversed, and I was totally unsure as to why, downward trends was upward trends in reality, and it'll melt your brain, these coordinate systems. Anyway, it now seems to be giving the right results, and yeah, it's of course open, and try it out and see how it goes.
Michelle?
Yes.
Again, Adrian, if I'm not mistaken, that albedo measurements was probably done with Magellan, the radar on board Magellan, and that was at 2.385 gigs.
Correct. That's it.
So I'm not sure, how does that correlate down to the 1299, or do you know? Or Does it make a difference?
It does. It makes a difference. It's relatively small difference from 2 gig to essentially 1, or from 2304 to 1190 or 1200. But it does make a difference. I did not attempt to formalize that in the notebook, because we're dealing with at least 2 frequencies for the different dishes. So that's kind of an open question on how exactly to normalize that, or if you even kind of can. And that was one of the things that we put into our application to the Green Bank Observatory was, hey, this would give us a chance to to maybe extract, with some successful radar returns, because you have to justify it with respect to science and engineering, and also, explain what you're doing. And so part of the science justification was this would be a really good chance to get, for the first time, observations at 2 different frequencies, with respect to albedo. We could use that. If all else being equal, then you can back it out and sort of obtain some results and show some differences in albedo. So that was one of the justifications that we put in there for things that we could potentially get from the data. Does that make sense?
Yeah. One other thing, and I'm not sure if it makes any difference at all, but that radar observation was SAR, synthetic aperture radar. Would
Yes.
that make any difference?
Not that I know of. No.
Okay.
No. I think that's the right way to do it.
Well, that's how they did it with Magellan. The radar on board was synthetic aperture. So I'm not sure.
Yeah, and for
With
those
just
that are
a
interested, there's 4 different maps. The reflectivity map is one of the 4 different maps. It's just an amazing amount of data from that data set. And it's really neat to look at. The reflectivity map, as you can see from the link analysis, is like false color, with like purple to yellow sort of. But the other maps are just, they're really quite lovely. If you're used to thinking of Venus as just a yellow blob, it's not. It's really neat. So follow the links and check it out. All right. And any other questions, Thomas, or any other advice or anything? I know that you're super busy with Artemis and all. I really appreciate you paying attention to the Eve work in the middle of all of that. But if there's anything else that you think we should track down or do or chase after.
No, I'll get back to it by next week and start reading your stuff properly first.
Okay. Yeah, your opinions and your experience here are extremely valuable and appreciated. So we'll just do our best, and anything that you spot that you want us to take care of or do, we're here for you. Awesome. Okay. So other things on the list that I have, we have a major BSides San Diego report. BSides is a cybersecurity conference, but it has a very heavy emphasis on do-it-yourself electronics, dealing with the physical world, and radio was a big featured part of that. So we had the honor of running the radio frequency village at BSides this year. So we had a full set of tables. What we brought was Opulent Voice demonstration, and we themed this as, this is what development looks like. So I would tell people, this is what your desk looks like when you're working on digital communications protocols like this. Here's the test equipment that you would have. Here's all these silver boxes. Here's all these little coaxes. There's a bunch of computers and like spewing data at you. Does it look messy? Yes, it does. and here's somebody, Paul, who very graciously agreed to field questions and to set this demo up and kind of expose all of the sausage making to the people. So that was one of the sort of the things that we brought. We also brought the RF Bitbanger. That's our HF QRP kit. And we were able to send 5 people home with a new kit, and very enthusiastic about HF QRP and digital modes on HF. This kit allows you to solder it up yourself. The surface mount parts are done for you. So that comes on the board, so you don't have to do surface mount soldering. The through hole and the winding your own torids are the things that you do. And then everything is set up and you get to operate if you have an amateur radio license. So let's talk about amateur radio and why you need a license in order to operate. You can receive pretty much anything, but if you want to transmit, you need your license. And we debuted W6 ORI. That is our brand new club call. So we are now also have an amateur radio club at ORI, and this was received very positively with lots of people enthusiastically signing up. We talked about our newsletter, and we also had a lunar descent CTF. So our capture the flag for the lunar descent. This is based on the Indian Space Research Organization's successful Chandra lander in 2023. And their implementation was on an FPGA, a single FPGA. The radar altimeter was written in VHDL, and they couldn't publish the source code, but they did write a really good article about this in IEEE AES journal. So we took that journal article with all the algorithms and we made a Python script. We noticed something right off the bat, that at low altitude, the FFT, you use less and less of the FFT and use zero pad because your chirp rate goes up. Well, when you get too low, well, your velocity is now nonsense. So I've just kind of given away the bug there. But, that has to be managed. And they did kind of heavily hint in the IEEE paper that that's what the deal was. There's also another interesting bug at the top. So with the very higher altitudes, you get gaps in the transmission. So our challenge was take our Python script, the implementation of Chandra's radar altimeter, and you make sure that your lander doesn't crash. So if you're going to hand off all your results from your altimeter just directly without doing anything to it to your autopilot, you have a problem. So this has relevance to self-driving cars. It has relevance in general to sanitizing input that you get. So you get raw input from telemetry. You've got to pay attention to that. And that is what the CTF required participants to do. And let's see, we also had Mesh Core. So we had someone from the community that set up a Mesh Core node. Okay, so in the process of all of this, we found out that the Opulent Voice, the recent fix for the missing 24 dB in the transmit chain, well, something strange happened. The transmitter now is working much, much better, but the receiver isn't. And I'm going to turn it over to Paul to talk about the demo and some of the stuff that we've done since then.
Okay, thank you, Michelle. I went in to the whole process of generating a demo for BSides with great optimism because we had just finished fixing the problem with the transmitter being too weak and had immediate satisfying good results. We were able to have voice working and short messages working seemingly according to spec. And so I figured it would be pretty easy to rig a demo with all this stuff that was already working great. And I decided to go one step further and try to rig a full duplex demo. So where two Libra SDRs were able to talk to each other. In order to do that, they had to be on different frequencies so they could listen while transmitting. So we picked a second frequency down in the 70 centimeter band and stuck with the 905 frequency that we've been using in the lab a lot for the first frequency. And that meant a new version of Dialogus that programmed the radios to two different frequencies. And I hooked it all up. My tradition for doing these physical demos at shows, which I've done quite a few of now, is that I don't set them up in my lab or in the remote lab. I take all the stuff that I think is going to be needed for the demo downstairs to a blank table and set them up just the way I'm going to put them at the demo. And that way I can't accidentally use something that's in the lab and not remember it. So everything, once it's working on my table, I can just pack up everything on the table and take it, and I have a pretty good chance of having that work at the show. So I did that. I cleared off a table, which is no mean feat, and put Libra SDRs down there with the recent software that had been successful and new Dialogus, and it didn't work. It didn't work. By this time, we got about a day left because I had figured, it'll just go together. I just had to gather all the right equipment. And I had registers that were generating nonsense. We found that problem with that. That was a problem where register had been inserted into the register map. So every register below that in the register map was now at the wrong address or a different address. And I'd not noticed, so I hadn't compensated for it in Dialogus. So those registers were looking normal and reliable, and they were generating bad results. It said it wasn't working, and I couldn't get voice or messages to go through reliably. But it wasn't completely broken because sometimes it would work a little, which rules out a whole set of things that could have been wrong. And I didn't succeed in solving all these problems before the demo, is the spoiler at the end of this. I brought the whole thing down to BSides anyway and showed it off. All the hookups were there. The data was scrolling on the screen from the debug, and you could see that something was trying to happen, but I couldn't actually make people put the headphones on and listen to how great the Opulent Voice sounds because I couldn't rely on it being there. We know a little bit about what's wrong now. We think we're on the way to solving these problems again so that things are working. It seems like there have been a lot of side effects that we had not anticipated in greatly changing the transmit amplitude, and maybe some accidental changes that crept in. I have a suspicion about some of that I believe now, strongly believe that those plausible looking register readings were not actually right. They were lying to me the whole time, which is why I was not able to make good progress in debugging whatever the problem turned out to actually be. And so right now we have a build working here in the lab that does receive correctly and generates the right data output, and the registers are swearing that it's not working at all. So those registers are lying, and I have only a guess as to why so far, but maybe by next week I'll be able to explain this in detail. So that's where we're sitting now. Opulent Voice took a giant step forward. I guess we can tolerate a step or two back, and we'll fix those things and move on. But there's always something going on.
Yes, there is the transmit change. So what happened on the transmitter was that we were missing 24 dB again. We have an article about that in the newsletter going out today. And that clearly needed to be fixed. That was a problem that we found once we went to go over the air, and we were like, oh, it's not just a little low, it's really low. And we did find out the problem. The problem was very clear that we were misapplying the bits that are used by analog devices in their DACs and ADCs. So we were shifting our own bits way too low. Okay, so where does that change need to be? That's in the modulator. That's fine. It's a submodule. Change that. But we also had to change the NCO, the numerically controlled oscillator. The problem that we're having with the receiver, because wow, if you're now just louder in your transmitter, no big deal, right? Your receiver should just work better, right? Okay, but the NCO that we had to change as well is instantiated in both the transmitter and the receiver. So these changes were then put into the receiver. Oh, well, I'll just back out those changes. So when I deal with it in the DMOD, I'll just shift it back down to where it should be mathematically. Well, all hell broke loose with bizarre shit happening. Pardon the language, but that has been the case since Sunday. So it is exciting, and I think that in the process of figuring out how to make sure that the transmitter changes or the transmitter changes and the receiver is actually properly receiving, that we will probably find a few other things that could be improved. So overall, this is really actually good progress. This change, the update needed to happen. But the fact that VHDL is really good about reusing designs, and if you change the base design or the root design, and then you implement it in both your receiver and your transmitter, well, if you have, if you've designed your receiver around a very quiet transmitter, then a lot of those control loops for the DMOD are going to be messed up. So anyway, that's what we're chasing after this week. This is all solvable stuff. It's almost working. I got every other frame to work, but that's not good enough. There's something going on with the timing. So by this time next week, we'll have a completely different landscape, and we may have some really good news by next week.
Yeah, let me say a little bit more about demos it shows, just in general. I'm fond of saying that nobody has done a convincing communications demo since Alexander Graham Bell. You know, he said, Watson, come here, I need you, and proved the utility of telephone communication. And ever since then, we've been doing the same demo over again. If it works, then you can say something into the phone, and that, the cat at the other end screams because you pulled its tail, as Einstein used to say. Um, so having a demo that works is actually not essential to having the demo be useful to the participants in the show. They see that you're working, and that complicated stuff is going on, and that interesting things are happening. That's what's important to these demos for the participants. The fact that it didn't work is important to us because having a working demo is much more satisfying, and it gives us a way to set a milestone and say, yes, we had it working by BSides, or we didn't have it working by BSides. So don't be afraid of doing demos live, as long as it's not essential to your message that they're working that day. I mean, if you're trying to sell something, you probably want the demo to be working. But if you're trying to convince people to come help you work on it, a non-working demo is almost as good. And what attracted just as many people, we were able to sit down and have good conversations about what we were up to and why. And I fielded a lot of interesting questions. For some reason, the younger people think that I might have some wisdom of the ages here. Maybe I need to dye my beard black again or something. But in the meantime, had some good conversations, and it was a very successful show from our point of view, even though the demo was not entirely working.
Okay, well said. All right. Any questions or comments for me or Paul or anybody else working on Opulent Voice? Okay, well that concludes our official agenda. So this is open discussion or office hours. Happy to entertain anything or anybody about any subject related to ORI's work or your work. So please speak up.
Here's something to
Very
show.
good. Go ahead, Rick.
That is one of the transmissions from Artemis 2 received at DSES and compared to a very interesting model of what we expected that includes Earth rotation and other effects, and they agreed quite nicely. I think DSES did a fairly good job up to that point with our data collection and analysis.
Yeah, very good. You can see an oscillation. That kind of proves your point.
That's actually in my report. That's a sinusoidal oscillation. And I have tried quite a few models to model that, and we haven't quite figured out what it is yet. I do have, let's see, wait a minute, let me try this.
Looks like a roughly 30-minute period for.
I'll have a lot more. I'm surprised you even noticed it, but yeah, that's good.
And for those that are watching that are wondering what DSES is, it's the Deep Space Exploration Society. This is one of the 34 stations that are on the sort of official list of Doppler observers for NASA Artemis2 mission. So what you saw was the Doppler curve or Doppler results from the Artemis2 mission from DSES. And yeah, that's the dish.
That's our dish, and then there's a lot of data here, but there's a copy of that same chart.
Yeah.
And here is some information about the residuals. And here is the residual that your sharp eye caught. And I'm trying to work on this to figure out just what it's all about. But it's, let's see, it's bounded by 4.5 hertz, 4.65 hertz of Doppler plus or minus. I don't know what it is yet. I was able to describe it, but and I've got a few equations here in my report, but I still don't have an explanation. What I do know, and you can't see until you read the report, is on the Doppler measurement is actually got a bias of about 3 kilohertz in it. And we track that down to a software bug. And that's what we have down here, the bias term. And we found out that the signal processing, the data collection software had a bug in it. And I've got a whole section here describing what the bug, what the correction to that bug will do. But I don't have a post-bug fix picture yet. So
Does that bias just moves the curve up? The negative,
it just
moves the whole curve
changes
up and down.
everything. Yeah, and so you can see I didn't change the model. We just put the whole thing 3 kilohertz up. So and let's see, it actually says in here what the bias term was. Where did it go? The bias was 1.3 parts per million. It was 2.935 kilohertz.
Okay. Wow.
And so we know what it is, and we're pretty sure we know why it is. However, what you don't see, because I'm not showing it to you, is chapter 1. What went right and what went wrong in here. And that is, we're not over.
Right.
So I don't have another picture after we fix the bug because we had the software fixed, and then the team that was out there physically monitoring the dish as it was steering came back and said, "Oh, we can't do this anymore." Turns out that all of a sudden, the dish will only turn in one direction of azimuth and not the other. And we said, "Oh my God, what did we break and how bad is it?" And we've had 2 separate teams out there so far trying to diagnose it, but fortunately, it does not appear to be motors and gears and chains and things. It appears to be there is an industrial, remember the good old days of industrial controllers where they controlled all kinds of things with 30 milliamp loops? Well, we have apparently such a thing. And all of a sudden, the load on the 30 milliamp loop is reduced, so it's drawing more current than is allowed, and therefore shutting down that one direction. And they tried looking at everything without success. And I said, "Well, wait a minute, why don't you just disconnect these wires over here that we're not using, because maybe the load is out in the old trailer instead of the control room." And they're going to try that today. But I will have more data because we have, so much to my surprise, a hugely dedicated set of volunteers, some of which I don't even know, who have been showing up every single night and every day to work on problems when they occur, and every night to work on collecting data. And tonight we have a team of 4 people headed by Bill who will be out there. And he said, if they can't fix this today, during the day, they will manually steer the dish.
Okay. Well, it sounds like a good solution. It's
we have the automated system
Yeah.
which displays on a screen in the control room exactly where to point the dish. And so all I have to do is every few minutes take the manual, we kept the old manual system, and all they got to do is track that with the manual system because the dish with the manual system operates perfectly normally.
Yeah.
It's part of this automated system that's gone bonkers.
Wow.
And so they're just going to watch that display and they've got to figure it out if they work in 2 hour intervals, if they that they can get some sleep and rest and so forth and work this thing all night long. And if they either get it fixed or do the manual steering, I should have some good past data tomorrow to analyze and build new charts and so forth and try to finish up this report.
Yeah. So people as a backup. That's
Yeah, and that's what we do.
yep,
We
you got to
have
do it. No, that's
and
amazing.
and we've gotten our membership has tripled in the last 2 years because we get people excited. We've been bringing in high school kids on a regular basis now from Eastern Colorado, which is underserved for STEM. We've been doing a lot of new work. It's very hard. And sometimes there's so much going on that it's hard to accommodate all of the things we want to do. But we're trying our best.
No, I think it shows.
So our plan right now, broadly, is finish Artemis, and immediately after Artemis, change the feed out and run the Dubas contest, and then switch the feed again and spend the summer doing radio astronomy, and then as we head toward October, put our EVE feed and equipment in and do the best we can with that. And this time we're hoping to better coordinate with our European partners in terms of frequencies and modulation and all the rest of that stuff.
Yep, sounds like a plan.
It's a lot of work for this year.
It is. That's right. Okay, any questions for Rick?
Yeah, Rick, this is Adrian. Like Michelle, the first thing that popped out at me when I saw that plot was that sinusoidal wave on it. And I don't know, it looks like the period on that is really long.
About a half
I'm
hour.
wondering, yeah, I'm wondering, could that be the spacecraft rotation?
I have
So,
no
so
idea.
sometimes they do the rotation for the like thermal equilibrium, and so one side doesn't get too hot from the other, and so forth, and or solar array pointing. And I'm just curious if what you're seeing is just the that very slow rotation of the spacecraft.
Well, I'm hoping that of the of the other uh, ground stations who recorded that particular pass or that particular transmission, perhaps eventually I will be able to find data that I can correlate that to and see if they have the same effect, or if it's something at our site that we did wrong, or if it's something about the spacecraft, but it would have to be that very same pass.
Yeah, I don't
And
think this is the same pass. This is
well,
the
that's a couple of days
yeah, it's a
different.
different day, but you can see that there's no obvious.
No obvious sign of that.
Yeah. So if we can, I'm sure that as more of the results come in, that if if the individual sites don't share the data themselves, that NASA will share a composite, data set, and then we'll, then we'll get an answer, or we'll at least see some overlap. I'm pretty sure that we'll get that. So nothing obvious here. This all looks like there is no obvious wobble here. That's all I've gotten so far, though, for results. That's what I've got for published data.
Yeah.
Cool. Yeah, no, this is going to be great. I think there's a ton that you can learn that we're going to learn not just about the sort of the art and the craft of receiving a signal and tracking a signal, but opportunities like that let you learn about your site and improve your site.
We have learned so much about the focus of our antenna, about how to properly configure the feed and how not to. We tried it both ways.
Yeah.
How to update this automated steering software so that it automatically gathers data in real time from the Horizon website, so that for missions like this where they fire a motor, and when they do, instantly all of the steering data has to change. We've got software now that automatically keeps track of that and keeps us on target, no matter what.
Yeah, very good. And all of this is going to be, I'm sure that are you the lead essentially for the reporting?
I'm the person of the person that the individual who interfaces with NASA.
Okay, well, we're looking forward to the reports. I assume that they're going to be published for us to
Well,
read.
everything we do is going to be, on the website or on the group's IO or someplace that yes, it'll all be published. I think my report needs peer review, but I may just throw it up there and let the world peer review it, because I don't know if I got any volunteers to do that.
Yeah, very good. Okay, well, we're looking forward to that. Oh, go ahead, Paul.
Oh, on a different subject. So are you done?
Yeah,
Okay. I wanted to show this. I don't know if we've shown this before on the video here. This is the imitation version of the FM comms board that Analog Devices makes to interface their radio chip to some of the bigger Xilinx development boards. We bought a couple of these so that we can reproduce the results that Aaron has created with OpenCPI. And I just wanted to mention that I just got started trying to do this. The BSides was in the way up until last weekend. This is an interesting device. This connector here is a standardized mezzanine connector for development boards, the FMC connector. Lots and lots of pins on that, but it just snaps in, and you have a high bandwidth interface to whatever's on this board, which in this case is an AD9363, I believe. So cute little board. It also has teeny tiny little connections here for the LO for transmit and receive. Those horrible little snap-in RF connectors that are only good for like 5 insertions. And there's another connector down here that says external clock. And I'm hoping I don't have to connect anything to either of those connectors. But if I do, I'll have to order some cables. But this is progress being made. I'm also over here. You can't see it, but it's on the other screen. I'm installing OpenCPI, which is one of the steps on the way toward reproducing these results. So maybe I'll have something to report soon.
Thank you. That's a big deal. Good for our satellite.
Yeah, what we have currently to test is a DBBS2 transmit. Just turn it on and it transmits. A demo of being able to transmit DBBS2, and we have enough equipment here to be able to receive that and make sure that it's correct. And then there'll be more later as Aaron continues to make progress.
Yeah, thank you so much. And also thanks to Aaron. And yeah, I'm really looking forward to this. All right, and I'd like to welcome Galaxy X S9 and Kolfla Naga and Victor Mansky. And all welcome to introduce yourselves. And if you have any questions for us or anything you'd like to talk about, you have the floor.
Yeah, Victor Mansky, part of the Southeast Michigan IEEE. And I lead as chair in the robotics and automation in aerospace, electronic systems, and communications. Obviously, I'm into FPGAs, so that's why I liked attending this session.
Well, thank you very much and welcome. And as a member of AES, then you undoubtedly have the recent issue of the AES journal or magazine where we got our lunar lander CTF idea from. So thank you so much for attending, and I hope this is I hope it's interesting. We certainly are dealing with the business end of FPGAs, and we talk about all of our trials and tribulations and bugs and bug fixes and everything that we're experiencing along the way.
Yes, wonderful. Thank you.
Hey, you bet.
Last minute.
Greetings.
Divine power. Tomorrow, divine power and God power and the universal law that support the opposite. But the truth is not reaching you because of the imperialist propaganda. I am of Algeria, but the propaganda is not. But in America and Europe, propaganda machine is very much here.
Okay, well,
and thanks for this course of FPGA. I've studied in electronic, but the messenger of message. And thanks.
well, thank you very much for attending, and we appreciate you very much. Reach out if you need any help with FPGAs or digital signal processing or figuring out how to get the most out of radio.
Thanks. Thanks very much.
You're welcome. All right, and Cole Flanage, want to introduce yourself or have any questions for us? All right, nothing heard, but I'll follow up with them if they're in the registration page. Okay, looking over my list, I think we hit everything. We sure do have a lot going on. The next major demonstration that we have is kind of a big travel, for at least for us here. So we are going to travel to Germany and to attend Friedrichshafen, or the big ham radio show in June. And this is a demonstration, a presentation to the European Space Agency to try to advocate for and try to convince them that a fully digital sort of FPGA-based multiplexing transverter type of amateur station for the next GEO amateur spacecraft is the right answer. So that's our pitch is that Opulent Voice up in a frequency division multiple access sort of scheme, and then handling all of the multiplexing and dealing with the different uplinks on the spacecraft, and then putting all of that information intelligently into DVB S2 and S2X frames on the downlink at 10 gigahertz. So uplink on 5 gigahertz, downlink on 10 gigahertz. That's our baseline design. That's the thing that they should pay attention to and advocate for, and help find commercial partners to put up the next generation of amateur radio satellite GEO spacecraft. So getting the designs to work as much as possible. It'd be really great to bring them an end-to-end demo from uplink all the way through to downlink. But honestly, any of the different sections working, the uplink protocol, Opulent Voice fully working, the spacecraft or space segment working, any of that working. That means a polyphase filter bank or polyphase channelizer working, which the work that we're doing on a smaller scale with AMSAT UK will be of great value, getting that demonstrated, or that demonstration itself would be a good thing to bring. And then the existing DVB-S2, S2X downlink working. So all of that's coming up. hopefully we'll be able to make it there and to be able to present and get good feedback and get it out in front of the community at Friedrichshafen. This is a show that really does kind of, people that go are interested in software-defined radio. There's a whole SDR forum at Friedrichshafen. So this is a pretty friendly crowd when it comes to digital communications. And the ESA being there with the Future Geo program, this is essentially it. This is their this is the workshop for the rest of the year. And after this workshop and after these presentations, they're going to make some decisions. At least that's the plan, as explained to me, for how this funded program from the ESA is going to go. So coming up in June, that's our next big demo, and that's what we'll be working towards. So that will include everything that's going on with Opulent Voice, everything that's going on with Hypharia, with OpenCPI, everything that already currently exists with the DVB downlink, that whole repository, all of the calls for help to kind of like tighten that up and work on that, and then integrating everything together. That's a huge task. So June is pretty much already here when it comes to looking at a complicated schedule like this. So we'll be bringing just whatever works and talking about the end-to-end kind of vision for amateur satellite. So it's looking forward. All right. Anything else before we close for the day?
Yeah, Michelle, this is Adrian.
Yeah, go ahead.
I ran across something interesting today, and this is sort of incidental to Opulent Voice, I think. And what it is, and I posted it on the chat. It's a link to a WAV file, WAV file, sound file, and what this is, it's a downlink decoded, originally encoded onboard audio on a LEO CubeSat. I believe it's called a spinny one or something like that. I'm sure you're familiar with SatNogs, correct? Okay, so this is off the SatNog's site. So this is a downloaded file that was digital and it was decoded, and so it's a WAV file representing the onboard recorded, I guess, message. And what it is, it's in Spanish. Okay, so you don't have to worry about necessarily understanding it, but just the quality of the recording. I think it's what's funny. Okay, it's kind of, well, how can I say, horrendous. and and so what it is, it's basically what the actual text is, or the I believe the beginning sort of paragraph or chapter or introduction or so forth to the very famous Spanish novel, the Don Quixote. So that's basically what they're saying in the file. Okay,
Okay.
but I think it's interesting if you listen, just how awful the audio is on that. And so, gosh, uh, now there's details on the SatNog site, such all the details. It's a very low bandwidth sort of downlink and so forth. So I can understand why it sounds so terrible, but it's kind of hilarious, kind of trying to listen to that. And
Well, that's the motivation for Opulent Voice. Well, one of them, but the one of the primary motivations for Opulent Voice was our dissatisfaction with the voice quality of digital voice of VHF and UHF. Almost all of the options, whether they're amateur or professional, were about a 3400 bit per second codec, voice codec. AMBI 1 and AMBI 2 are the big ones that are chosen by both amateur and professional commercial radio solutions, and even the one of the most famous open source voice codecs, which is codec 2, tops out at 3400 bits per second. This gives you a voice quality that's barely acceptable to listen to. It's really fatiguing to listen to it very long. It's hard to recognize voices over, distinguished voices. It's intelligible, but it's just intelligible. And we decided that that level of voice quality was really not good enough, which is why Opulent Voice uses Opus voice codec at 16 kilobits per second, and that's pretty darn good. We could probably go higher, but the choice of 16 kilobit per second was on purpose. We only have to give up 2 meters. It's legal in almost every country at 70 centimeters and above. And the voice quality is much better. It really relaxes the major complaint that all of us have. When you look at professional communicators like dispatches, public service and emergency communications responders, for years and years in all surveys, the main complaint about P25, which is the main protocol used in public service, the main complaint was the voice quality is terrible. You constantly hear fire and police and EMS asking for a repeat, especially if there's any background noise. And you know what? We just deserve better. So that the voice quality was the main motivation for doing Opulent Voice in the first place. We are really happy about the results. We're very confident that this will make it stand out from all of the other protocols in a major way. You do have to have a higher bandwidth. There's no replacement for displacement, as they say in automotive. If you want more horsepower, you need a bigger engine. So you do have to pay. It's 81 kilohertz from null to null for our Opulent Voice signal. But the benefits are enormous. The other major motivation was we did not like the second clunky packet mode that you had to shift back and forth between voice or do fussy things to get keyboard chat or data or control signals in your stream. And so that's why we integrated it all with queues and priority queues, and it's working. So that's kind of why. So yeah, thanks for mentioning this, because it's a really perfect sort of it encapsulated very perfectly why we really like for communications, especially amateur voice communications and digital communications at UHF and above, to be much, much better. We can do it.
I listened to a few seconds of this recording, and it does not appear to be a vocoder at all. It sounds like a voice synthesizer.
I'm not sure exactly how that was encoded up on the CubeSat. There might be some more details there in the sat nogs. There's a whole discussion on how to decode this stuff, and I believe the satellite was also sending out some pictures. And boy, I don't know what you're looking at when they decode those pictures. I can put maybe the link on that discussion from
Oh, yeah.
sat nogs if anybody's interested. Let me see
Yeah,
if I
that'd
can
be
just
good. Yeah, if you can go find the thread on
yeah.
the forum, that'd be really fun. I don't object
Yeah.
to LEO satellites reading me books at all. I would actually like a lot more of that in the world. That would be fantastic. But it does have to
Yeah.
have better voice quality than that.
I, I don't know if you had a chance to listen to that, but it's almost hilarious. Let's see. I think this is the link for the discussion on that, and I'll put that on the chat there.
Thank you. All right. Yeah, I'll
Yeah.
make sure that gets into the recording too. Yeah, another thing that I've learned through this project. So Interlocutor is our, the human radio interface, and it runs in HTML5. It's a browser thing. So Python script starts up a web interface, and that's how you interact with our radios. You just target the radio has an IP address, you target it, or you target, a computer running in Interlocutor, or a satellite simulator or whatever. Long as it has an IP address, an Ethernet connection, you can talk to a modem, you can talk to a satellite, whatever. In doing this, we wanted accessibility to be very important. And if you can't see, or if you can't look at a screen because you're doing something else, then text to speech becomes really important. The standard text to speech took a lot getting used to. Most people that routinely use text to speech, the voice is very robotic sounding to me. And most people crank up the words per minute. So when you first hear it, it sounds like gibberish. It doesn't sound like nice text to speech. But you know what? You get used to it. You can actually adapt to it. So that was one of the things that the people advising me about accessibility explained. So so we do have text to speech, and we also have the other way around. If you are in a situation where you want to use interlocutor, you want to use our radio, and you can't have noise, and if you're trying to be quiet, you don't want to disturb other people, then we have audio transcription. And this is not done from a central server. It's actually done there locally. It's a really nice, interesting sort of neural network approach. and it's pretty good. So it can handle accents, I got to tell you, and it can handle low audio and people muttering or incomplete sentences or jargon. And it works pretty good. It also gives you a confidence, so you can tell like it's just guessing about the transcription versus, I'm very confident about it. So we have both directions. But just in working with the different accessibility requirements and communities, I've learned an awful lot about voice quality and the things that I would kind of assume would be useful. The very fast robotic sort of text to speech, you can adapt to this pretty quickly. At first, it sounds like it's of terrible quality, but that's kind of the way it's done. All right, so I'll make sure to copy the links that folks have shared today when we are going to publish the today's meeting recording. So I'll make sure that all that is there. And so I'll turn it back to you all. If there's anybody that has anything to share or any other questions for the group, or anything you think we should be paying attention to, then the floor is yours. All right. Well, I'd like to thank everybody that has contributed reports for today, that is working so hard on very ambitious things in open source. Your time, once you spend it, can't ever get it back. So we appreciate you being here today and sharing a little bit of your day with us and listening to all of the things that we're doing. And if you're interested in learning more about our work and being part of our community, then please go to openresearch.institute/getting started or getting-started, and we will we'll help you get the most out of open source and digital radio and amateur radio. We just want you to get the most out of it as you possibly can. So thank you all again for being here today, and we'll do this again next week, if not before. If you have a project or a question or any sort of ideas for us or any feedback on any of our published work, then your comment and critique is welcome and encouraged. All right, see you all later.